All right. Okay. Uh, Hello, everyone. Welcome back to Comp 3430 Operating Systems. Um, I like immediately upon entering this classroom and trying to get this stuff set up, I'm like feeling this terrible I don't know, like post-traumatic stress situation where like over the over the break I had this dream where I came to class and I was trying to get set up and I couldn't get OBS to work. Like I don't know what happened, something just reset in this thing, and I get to class today and I'm trying to get my laptop connected to U of M Secure and it's just not happening and I don't know why. Like I was connected in my office and I'm really grateful for your offer to do the hotspot, but I'm connected to U of M Guest and I'm hoping that I don't get kicked off of U of M Guest in the next 40 or 50 minutes while the live stream is running, but it shouldn't be a problem. Welcome back, everybody. I hope that you all had an excellent break. This morning is feeling, I don't know, it's really nice. Like when it's 4 degrees above in the fall, it feels like that cold that chills you to your bone. But when it's 4 degrees above in the spring, it feels like a nice, like a beautiful warmth that's just like, it's happening. Spring is coming. It's great. So I'm really, really happy about that, despite the issues with getting connected to Wi-Fi this morning. So what I want you to be able to do by the end of today's lecture is first, I want you to be able to know a little bit more about Assignment 2. I want to spend some time talking about Assignment 2, what you're expected to do for Assignment 2, and the kind of stuff that you have available to you for that. I want to then also continue to work a little bit on pipes. The stuff that I want to work on with pipes today is 2 weeks ago, we did the happy path with pipes. Like I wrote some code in front of you that took pipes and passed information from a parent process to a child process. We did some cool stuff with that. Like we had the child process execing a new program and having that new program read standard input, but this was something that we used that special function dup2 to manipulate our file system, our open file table in the files in the operating system. But while the happy path is great, I also want us to see what happens when it's not so happy, and like what kinds of things we can try to do to figure out what's happening. The main thing that you're going to see with pipes with the non-happy path is stuff will get blocked and it won't be clear why things are blocked. It's just like stuff's going to get stuck in the middle of something and it's unclear who is waiting around and what they're waiting around for. So my goal today is to take us through some code that will show this problem and then the steps that we're going to take to try and figure out how to get out of that situation in the first place. So let's immediately start taking a look at assignment 2. So assignment 2, I posted this a little bit earlier in the break. There's a couple of components that I want to take a look at with assignment 2. And the first part is going to be the assignment description itself. So what I want you to do for assignment 2 is I want you to build a shell. And I want you to build a shell around the file system code that we wrote for assignment 1. If you squint really, really hard, what we're starting to build here is something that looks like Docker, if you're familiar with this idea. The thing that we're really building is something called a chroot. So this is a change root. We're kind of like making a process that thinks that its root file system is something that's not the actual root file system. But I want to be like 1,000,000,000% clear that you really got to squint hard to make it look like Docker. This is not Docker. This is a very bad version of Docker if it's even an imitation. But it gives us that same sort of idea. And so what I want us to do is have an interactive shell where we're given a volume that has code on it, binaries, programs, and I want us to be able to read those programs from this volume and then run those programs in the system that we're running on. This is going to have you using system calls to create and manage processes. So you're going to have to do things like fork and exec and wait with the code that you're working with here. And then one of the features of shells that we're going to be using here is I want you to be able to implement pipes between processes. So I want the standard output of one process to be the standard input for the next process in the pipeline. That part has nothing to do with the file system stuff. It's just loading the programs up that's going to be part of the file system stuff. The general requirements for this assignment have not changed from the first one, so you're welcome to remind yourself of these requirements, but they haven't changed themselves. I'm not going to tell you about this. I'll let you read this part on your own. This is me just telling you about what the word shell actually means in terms of the way that we're using our machines. I'll let you read this on your own time. What I want your program to look like is if I run this nqp-shell and the one argument that I have to pass it is a volume, an exFAT formatted volume, then we should immediately get a prompt. And from that prompt, we will be able to do different things with the files that are on this volume and launch processes from the files that are on this volume. There's a few things I want you to do to begin with. The first is I want you to write some built-ins to your shell. A built-in program in a shell is one that doesn't do fork and doesn't do exec. So this is it's not a program, it's like a program. You're going to basically read standard inputs, compare it to CD, and then just like have code in your main file that does this change directory action. Change directory is something that's going to allow you to manipulate the working directory for your shell. So when we're running our shells, we always have a working directory. This is where we currently are in the file system. When we start this shell, your working directory should be the root. It should just be / and then CD should allow us to change into directories that are in the root directory. I'm explicitly telling you that we're not going to do this kind of a thing. I'm not going to put like dir1 / dir2 / dir3. It's always just going to be one directory in the current directory. And we're not going to have like nested directory structures to have to worry about. Your CD should also work with changing to the parent directory. So go back to where you were before, but you don't have to worry about things like having special support for the current directory. You don't have to support going to dot, for example. If we try to change to a directory that doesn't exist or isn't a directory, your shell should print out some kind of a meaningful error message to explain that you can't change to that directory because it doesn't exist or it's not a directory in the first place. PWD is a command that should just print out what your current working directory is. So if I type in PWD, I should get immediately when I start the shell, it should be /. And then ls should list the contents of the current working directory. I am giving you explicit permission to just copy and paste the code from ls.c into this. You don't need to write this code yourself. You are more than welcome to just take my code and work with it for implementing this, this built-in. The launching processes part, what I want you to do with this is I want you to start processes that have binaries that are in the volume. So I'm going to open this right now. This link takes us to sorry, this isn't what I wanted to open yet. This will take us to a description of the volume, and I'll show you that in a second. What I do want to show you right now is that we've got way down here a template repository that you can start with. So here I've got the nqp-shell.c, the root image that you should be starting from, the header from the last assignment, and then a precompiled version of this exFAT implementation so that you have something to start with here. You don't have to use your own code for this assignment if you don't want to. You're very welcome to use it if you want to, but you're not required to use it. This is a version that I compiled from my code for on Aviary. So I'm going to go back up here to where we were at with launching processes. We're going to be using some Linux-specific system calls to be able to do this. So when we're working with these volumes, our operating system, Linux, Aviary, it doesn't know anything about the file system that's in that file. It has no idea that there's an exFAT formatted file system in there. If we wanted to work with this as a regular volume on a Linux system, we'd have to run the command mount to be able to do that, to take that file and put it into the current hierarchy, the current file system tree. But we don't have permission to do that. You and me don't have root permissions to do that on Aviary, so we're not going to do that. Instead, we're going to be using a combination of the exFAT code from assignment 1 and then 2 Linux-specific system calls. The first one here is memfdcreate, and the other one is fexecve. Memfdcreate will allow you to make a file, big air quotes here, a file. It's just memory backed. It's not actually making a new file in any file system, but it's giving you a file descriptor. And a file descriptor is something that you can write to. You can write to a file descriptor. fexecve is a system call. It's exec, but instead of a file name, it takes a file descriptor. So to work with this, what you're going to be doing is calling this memfdcreate to get the operating system to give you a file descriptor. I want to have a file descriptor. Then what you'll do is use nqpopen and nqpread to read from the volume into the file descriptor. So you're going to do nqpopen, nqpread a byte, and then write to this file descriptor. Read a byte, write to this file descriptor. Read a byte, write to this file descriptor. And you are very welcome to copy and paste the code from cat.c to do this. You don't need to write this code yourself. You can copy this code from cat.c. Then, once you have fully copied the file from that file system, you should use some combination of fork and fexecve to launch that process. That will then get the operating system to take that memory file and start running it like it's an actual program. So from the root directory of the volume that's provided, I should be able to run this command. I should be able to type in echo and then hi. Echo is a program that's in the volume. You should launch that echo, pass it the arguments in the call to exec, and then it should print out hi to standard output here. And this is just the regular standard output that we're looking at. This is going to be the basic implementation of your shell, is the built-ins and then these running single commands by themselves. Building upon that, I want you to implement input redirection. Input redirection is something that you probably saw in 2160, question mark. Yes, everybody knows what input redirection is. Many people are giving me nods and thumbs up. If you don't, take a look at this link here, this redirecting input and outputs. This is a textbook for tools and techniques in computer science. It does a pretty good job, I say, having written it myself, of describing what input and output redirection are. So if you're kind of forgetting or fuzzy on what that was, take a look at that there. You should be able to redirect a file to be the input for the first process launched in a single command by your shell. So if there's a file that's called hello.txt in the volume, I should be able to change the program cat in the volume, its standard input, to be that file. So just like you're reading cat from the volume into a file descriptor that's backed by memory, you should also be reading hello.txt from the volume into a file that's backed by memory. So this is going to be that memfdcreate. In this part, what you'll do is you're going to use that dup2 system call to manipulate the open file table for the process you're about to launch to replace its standard input with the file descriptor for the file that you just read into memory from the volume. When you get to implementing pipes here, which, again, everybody's seen pipes? Yes? Question mark? Has anybody not seen pipes? Okay, everybody's seen pipes, awesome. Everybody that wants to say that they've seen pipes have seen it. But again, there's an article here in this Tools and Techniques textbook that kind of describe that to you. What you should also be able to do as you're building upon this is to have pipes between these commands in your shell. So I should be able to run cat here, replace its standard input with hellos.txt, pipe its standard output to be the standard input for this program that's called head, which is also in the volume. Head is a program that will just print the first n lines that we tell it to print and then stop printing lines. And then it should basically have these two processes running and communicating to each other through pipes, and then printing their output to standard output in the end. The very last part here is I want you to have a way to write the final standard output to a file, to duplicate it to a file. With input redirection, we're loading things from the volume itself to replace standard input for processes. But in that we haven't done write support for this file system, and I don't want to make you do write support for this file system. You can thank me for that later. I want to have output being written to a file that's not inside the volume. So duplicating the output from the shell itself to a file. The way that this is going to work is that if I ran that same command above, so here, if I ran this here, then my log that I have written to log.txt should have this as its contents. It's not going to have the command that's written there because you all never actually wrote that to standard output. That was just something that was typed in on the keyboard, and that's the standard input for a program. But the standard output itself never actually had that printed to it. This is going to be similar to pipes in that the very last command that's written out should have its file descriptor for standard output replaced with an actual file, and then it will write to that file whenever it does any writes. The template that I've given you here contains a start of a shell implementation. So this is something that you're free to start working from here if you want to. I did make one change to the interface for assignment 1, which is I added this additional function down here called vol label. If you do want to use your own code for this, you'll have to implement this function. Implementing it is straightforward. This is just going to be the volume label directory entry from the root directory of the file system. I'm using this so that we can have something that's a little bit nicer of a prompt than just printing out like nothing. So the shell here this is where our main loop starts to happen for the shell, is to read standard input here. Someone has already asked me to provide a version of the .o file here for M1 Macs, and I've asked them to email me, so I'm hoping they email me so I remember. I don't have an M1 Mac on campus, but I do have one at home, so I will recompile it and I will share that in this repository for you so that you don't have to constantly work on Aviary if you are running an M1 Mac or any kind of Apple Silicon. Which kind of brings me to a related, will you give us the .c file for this exFAT implementation? And I kind of have a philosophical standpoint on this, that I'm very happy to have you come and talk to me in my office about my implementation. I'm very happy to show you my source code in person, but I'm not going to distribute my source code for this last assignment. It used to be based entirely on, I don't really like it when my source files show up on Chegg and Course Hero, because that's kind of like violating my copyright. I don't want people to steal my work, and I don't really want to have it up there for students to find and use for academic integrity violation purposes. But in the last couple of years, there's this really cool product that I think we all know about called ChatGPT, and I'm philosophically against OpenAI and other AI companies training their tools on my intellectual property. I just don't really like that. I am very, very happy for you to come and sit and talk to me about my implementation. If you're not able to make my office hours, please make an appointment. I'm very happy to talk to you and show you what I've done and like guide you through getting yours working if you want to. But all of that said, I don't want that to be an impediment to you not being able to do this assignment. And so I'm giving you this precompiled version, and I will give you an additional precompiled version for M1 Mac so that you have that available to you if you need it. If you do find any bugs in this, please let me know. Please let me know as soon as you can so that I can fix the bug and republish a new .o file. But yeah, I want to make sure that that's not an impediment to getting started with that. The volume that I've given you, you can assume that this is what the graders will use. It contains this. In the root directory, there are some programs So echo, grep, head, sort, tail, and tr. And then there's two, and cat, and then there's two files called hello.txt and hellos.txt. And there's one single directory that contains, that's called dictionary words, that contains a copy of each of those same programs and also a file that's called words. Words is the Canadian English dictionary that comes from Ubuntu's standard repository. So this is not a file that I created myself. In terms of your implementation, this explicitly will only work on Linux. If you're using Mac OS, you will either have to use Lima to do the part where you're doing the mmfd create and the fexec stuff, because these are Linux-specific system calls. So you'll either have to use Lima as a virtual machine, or you'll have to work with Aviary for that. And then the last thing is just a little note here is that all these programs that are in the volume, they're not actually binary files. They're all just shell scripts. And Linux, when you do exec on a shell script, it will just run the shell script for you. So this is kind of a convenient thing for me. I don't have to rewrite all these programs. And I can just give them to you as these little shell scripts. For the evaluation of this assignment, there's 25 total points, and I have a little bonus for this one if you want to work with the bonus. So there's a total of 27 points eligible to be awarded. Bonus points, the way that these work is that within a category, so within assignments, for example, you can get more than 100% on one item, and that will just be redistributed to other items that are in that same category. You can't get more than 100% in the course. Unfortunately, the university doesn't grant A++. Despite what my grade 3 teacher told me in science class. Yeah. So if you get to that point, it gets redistributed around the other assignments. And then there's the same kind of things as there were for assignment 1 with the graders. So they're going to have some latitude to make adjustments within the levels of each of these things. In terms of the assessment, I kind of suggest that you do it in this order that I'm describing the rubrics, because I think that this naturally lends itself to building things up from scratch. So for the built-ins themselves, there's not many points that are available for this because I'm basically giving you permission to just copy a bunch of my code, and that's not writing a lot of your own code for that. So I'll give you some credit for doing the work and getting things working here. And it's kind of just like getting stuff set up and being able to change directories and list the contents of directories. In terms of launching processes, I'm kind of looking for you to be able to build stuff up for this. And all of the things that follow here are kind of interrelated. So the assessment of input redirection, the assessment of pipes, and the assessment of logs are all affected by your ability to launch processes, which kind of makes sense. If you can't launch complex processes, you can't do input redirection in the first place. Same thing with pipes. So in terms of launching processes, what I'm looking for you to be able to do initially is just make an attempt to get memfd working with NQP read and write. So copying the binaries into memory and then asking for them to be read. And then eventually what I'm looking for you to be able to do is fork and exec and wait. So to be able to actually run a process and then have your shell regain control after that program has ended. Input redirection, same kinds of approach. You know, initial implementation starts with memfd create and then working up from there. So starting to be able to actually have input redirected for the very first command in a pipeline. Assessment of code pipes is kind of the same thing here. So I want you to be able to either start with reading from standard input and then pressing Control-D on the keyboards up to the point of having arbitrary number of processes, and standard input is redirected for the first implementation, and the logs is kind of the same thing here. The bonus implementation here is your shell doesn't have to support like up arrow to get commands back and editing the commands that you've written. If I touch the arrows on the keyboard in your shell, it's just going to print weird symbols. Like it's not going to work the way that we're expecting it to. So the bonus here is to start adding readline support. Readline is a library that you can use to do line manipulation, so working with arrows and stuff to be able to edit the command as it's being typed in. The bonus is worth 2 points. It either works or it doesn't. And this is me. I'm going to assess the bonus part of this. So I'll give credit where credit's due if you put some effort into this. Yeah, and then the submission of the assignment is the same. This is just like submitting assignment 1 with Handin. So I've just thrown a lot at you in 20 minutes. Kind of like with the last assignment, I'm going to save some time for questions in the next couple of Fridays. And so I'm not going to have any questions right now, but the assignment forums are up. And then, like I said, I should be making a change to the repository to have an Apple Silicon version of the .o file, so that you have something if you're working with a Mac. All right. Okay. So let's go back to thinking about pipes. Signals. They were kind of cool because we could start doing this interprocess communication stuff. And really importantly with signals, we were able to send information or send signals between processes that were not related to each other. So I could have 2 completely different terminals open, and I could be sending a signal from one program that has no relationship with this other program that's open in this other terminal. But they're limited in that we can't really send much more than, hey, this event has happened. There's a bunch of information that we can send, like who sent it, but it's not like user controllable. I can't tell the operating system what to send in this signal. And so we built upon this to start using this thing called pipes. And pipes let us send stuff, and that's really good. The problem with pipes is that pipes can be quite finicky. They can be quite finicky, and they can be baffling to try and debug because they wind up leaving us in states that don't give us a lot of information about what's going on with those pipes. So I want to write some code. I've posted a version of this code up on that interprocess comms repository. So if you have this repository and you want to code along, then please pull it. If you don't have this repository already, please clone it. I'm going to start by doing that right now. So is that big enough at the back? OK, awesome. I'm going to do git clone, https code.cs. umanitoba.ca comp3430 winter 2025 interprocess comms. I'm going to change into that, and the file that we're going to be taking a look at here is called frozenpipes.c. So I'm going to edit frozen pipes. I'm going to pop open a new terminal, and I'm going to change into the same directory here. And I'm going to double check that I'm in the same directory here. I am indeed in the same directory. I'm going to make this, and I'm just going to run it. So the state that we're in right now is that in our main function, we have pipes that we have initialized. We've passed this array that has 2 integers to the pipe function, and it has populated them. We've got fork. We are duplicating our process control block, and we're getting different values put into that return register for each of the 2 copies that we have. The child process is reading from the pipe. It's reading from the read end of the pipe, and I've established here in my own code that end 0 of this array is the read end. There is no read end of a pipe. I'm just saying end 0 is the read end of this pipe. And all I'm doing is reading 1 byte and printing 1 byte. That's all this code does. Once I finish that, so once read returns and I get 0 bytes read, then I'm just going to exit in my child process. In my parent process, I am writing to the right end of the pipe. And again, I'm kind of just saying end 1 is the right end. I am internally agreeing with myself. Yes, 0 is the read end and 1 is the right end. I'm writing 3 bytes to it, the string HI exclamation point. And then I'm printing out this message, and then I'm waiting for my child to exit. So I'm going to wait here. I'm going to block here until my child has exited. This code looks pretty sane. It looks pretty reasonable to me. It looks like it should terminate. It looks like it should terminate, and yet it's not terminating. In fact, I'm going to run PS with a new option here, F. And what f does is it prints out a tree for me. And what we can see here is that fish, here is my shell. It has forked and exect this frozen pipes. Frozen pipes has forked. And there's two processes here. And the state that they're both in is this S plus state, which again, this is us hand wavy saying they're blocked. They're just stuck. They're both waiting around forever. They're both waiting around forever, and they're never going to terminate. They're just stuck here. So what I'm going to do with this is I'm going to hit Control-C on my keyboard. I'm just going to terminate them. I want them both to stop because they're never going to finish. They're just going to sit here forever waiting for each other. And I'm going to go through my thought process here. So my first thought process is, well, maybe write is getting called in my parent process, maybe, before I've been able to call read in the child process. I want to stop here right away and say, this is my thought process, but it is super wrong. It is super duper wrong. This is not the case, but this is my thought process. And so what I want to do here, I think, is I would like to make a change to this so that what I'm able to do is synchronize these two. I want to make sure that read gets called after write. I want to guarantee that that's going to happen. So what I'm going to do with this is I'm going to start using this child ready signal handler that I initialized up here. And this is incrementing this flag variable. So this is looking pretty similar to what we did before. I'm going to make sure that my child process is able to send the message to the parent, and the parent is able to receive that message by registering the signal handler before I call fork. So I'm going to say man2 sig action because I can't remember the way that this is supposed to work. So I'm going to say sig action. I'm going to pass the signal that I want it to handle, sig user1, and I'm going to pass the child ready as an address, and I'm going to pass null as the last thing. I don't really care what the old action was. I'm going to register the signal handler. Then what I'm going to do is my child process is going to kill the parent process. And I got to make sure, because I always mess this up. The first one is the PID. Okay, I already messed this up. The first one is the PID. So I'm going to say get ppid. I'm going to send the signal to my parent, and I'm going to send it sig user1. And what I want my parent to do is I want you to waiting for child to be ready. While flag is equal to 0, spin around. Just do nothing while the child has not signaled to me that this thing is ready. I'm going to make this. I'm going to run it. But we're still just stuck here. We're still just hung. My theory with this, I'll write this right here. Theory, maybe read is happening after write. Let's use signals to synchronize the parent and child. Child's calls to read and write. Important, this is not the right path. This is not the right path. This is not the right path. Pipes don't work that way. There is no real ordering of like when you call read and when you call write, other than if you call read and there's nothing to read, it will block. if you call write and nobody's read it, it's just going to get kept in a buffer in the operating system space. There's just an array in our operating system that just keeps that data around until somebody actually calls read on it. So this is not the right path. It seems to make sense, but it's not actually the right path here. So what I want to do instead is I want to start using a program that's called strace. And we have seen strace before when we were starting to look at working with files and trying to think about processes and what system calls they're making. I'm actually going to zoom into this shell, and I'm just going to hide the code for now because the code actually isn't important for what I want to do with strace here. You can run this on Aviary. And what I'm going to do by default here is to run strace with frozen pipes. So we run strace, and then we pass it the program that we want it to run and intercept all the system calls for and print stuff out for us. So when I press enter here, we see all that ton of output that we had seen before the first couple times that we worked for this. And we're also kind of seeing some interesting stuff. Like what we can see here is that we're stuck on wait 4. Wait 4 is a different system call than wait. That's what's actually getting invoked underneath when we call wait with null, but we're just stuck. We're just stuck waiting for this child process to finish. So that's like helping reinforce the observations that we've made already here. I'm going to hit Control-C on my keyboard. And what I'm going to do is, first, I want to suppress a bunch of the output from strace because there's too much. Like, there's so much information here that's not actually useful to me. And so what I'm going to do with strace is I'm going to pass it this new flag that's called -e. And -e is going to allow us to specify what system calls it should actually print out. So I'm going to say -e trace equals, and then I'm going to pass it first %processes. You can read about all these different flags that you can pass to strace in the manual page for strace. I'm just going to tell you the ones that I'm using for this. If you want to read more about them, you're more than welcome to read more about them. This %processes here is a filter for I only want you to print out system calls that are related to process management. That's all I want you to do here. So I'm going to hit enter here. Not processes. I'm going to hit enter here, and now immediately we have way, way less output. Good, awesome, like this is great. We immediately see execve. All right, cool. That's my shell calling execve on frozen pipes. In fact, it's actually strace in this case that's calling execve to run that frozen pipes program. That's cool. Clone here, this is my program calling fork. On Linux, we don't actually have a fork system call. When we call fork, we're actually calling this clone system call underneath. And what we get back from clone here is the process ID of the child process that we launched. Okay, that's really cool. Then we've got SIGUSER1. So that's actually telling me I received a signal. I handled this signal, and I started to do stuff. My parent process did indeed receive that signal. It did something, and then it got stuck at wait. I'm going to hit Control-C here to terminate this again. And I'm going to add to this. So we had %process. I'm also going to add DESC. This is for filter system calls that take file descriptors as an argument. And I'm going to hit enter. And there's a bunch of that extra stuff from the beginning again, like all these mmap calls that we don't really need to know about. Although one thing I'm going to point out here really quickly is this read system call here. This reads this 177ELF. This is actually the code that's reading the frozen pipes binary file into memory right now. That's awesome. I think that's super cool. And we can see that because ELF here, ELF is the format for programs on Linux systems. And this is the magic number or the magic description of an ELF file on a Linux system. But when we get down here, we can see here I called pipe. I called pipe in my parent process before I did anything. And what's really cool about this is I can actually see these are the numbers that are the file descriptors that I got back. So when I called pipe, pipe2 is actually being invoked underneath, kind of in the same way that when I call fork, clone is being invoked underneath. When I call pipe, pipe2 is being invoked underneath. And these are the numbers that I got back from my file descriptors. And what I can also see here is write 1, standard output, waiting for child to be ready. Write 1, standard output, about to write to the child. Write 4, high. Now I'm writing to the right end of that pipe. And I can see which file descriptor I'm actually doing this write to. But again, we're just stuck on wait here, and it's not really clear what's happened. Importantly, everything that we're seeing here is in the parent process. This is just the parent process that we're seeing right now. So I'm going to hit Control-C on this one last time, and I'm going to add a new flag to this called follow forks. Follow fork says when fork gets called, follow it. Like, follow the different processes that get launched by this, and then also trace their output. I'm going to hit Enter here, and the output has changed. There's still all that extra stuff at the top. There's a bunch of stuff here that starts with mmap. We can see here, I called pipe in my parent process before I called fork. And I can see that I still get file descriptors 3 and 4 from the pipe system call that I made. I called clone here, and I got back 51188 in my parent process. Then I've got 2 processes, 51187 and 51188 here. And I've got their output interleaved because they are running at the same time. They're literally running at the same time, so I withdraw my air quotes. They're actually running at the same time. They're literally running at the same time. And our parent process here writes to standard output, waiting for child. Our child process, waiting for parent, message from parent. Our child process calls kill, and it passes to 51187 sig user 1. Our parent process acts on the signal. The child process regains control. The child process reads 3 and gets blocked. The parent process about to write to child, the parent process says write, read is resumed, and we got an H. Okay, cool. Read was resumed from read 3, the read end of the pipe. Okay, cool, yes, awesome. 51187 says message sent. All right, it sent the whole thing. Read 3 is blocked, unfinished, wait 4 is unfinished. Read resumed, exclamation point, blocked. Okay, so the child process did actually read everything that we sent to it, but it didn't print it out. I'm going to hit Control-C on my keyboard. I'm going to zoom out of this, and I'm going to go back to my code here. I'm going to comment out this line right here, and I'm going to uncomment this line. I'm going to make, and then I'm going to just run it without strace. Oh, okay, awesome. Yeah. So our child process did actually read that. This is an important note here. Note put char and all of stdio will buffer input until a new line character is printed. And I never printed a new line character. I never sent a new line character in this pipe. If I happened to send a new line character, it would have just worked. I might have set this up intentionally. It's going to buffer this input. There's an array inside of the standard C library that's just keeping track of everything that's been printed, and it's only going to actually write it to standard output when a new line shows up. But we still have a problem with this. We still have a problem that is, there's still 2 of them, and they're both stuck here. They're both sitting around waiting for us to do something. So I'm going to go back up to this shell. I'm going to hit Control-C to terminate these processes. The problem that we've got right now is that read here on line 41 in our child process will block while there is any write end open to the pipe. It's going to stop and it's going to wait here. if anybody could possibly write to the right end of this pipe, I have to wait around until nobody is left to write to that right end of the pipe. And so you might notice from this, I didn't close any ends of pipes. And I did that on purpose. I super did that on purpose here. I didn't close any ends of pipes. I've got my child process waiting for a message from parent. It's reading, it's writing. And then I've got my my parent process writing, but there's no closing ends of pipes here. So let's start. Let's start closing some ends of pipes. Immediately upon returning from the fork call here, I'm going to say close FDs at 0. Parent process never reads. I'm going to make this. I'm going to run strace, and I can see that I did actually call close in my parent process somewhere. I'm going to hit Control-C. I'm going to make this again. Yeah, I did. Close is way up here at the top. That's why I couldn't see it. So I closed file descriptor 3 in my parent process, but we're still stuck. After the parent process is finished writing, I'm going to close FDs at 1. I'm done writing. Let any reader know I'm done. I'm going to make this. Now think, just in your brains right now, is it going to work? The hint obviously is no, it's not going to work because I'm asking you to think about it at all. I'm going to run this, and I'm still stuck. I'm still stuck. My problem here is I'm going to go back up to the top. I call pipe on line 23. I call pipe before I call fork. When I call fork on line 36 here, my process control block is duplicated. The whole thing, including the open file table. If the whole thing, including the open file table, is duplicated, that means that I actually have 2 read ends and 2 write ends to my pipe. 1 read end in the parent process and 1 write end in the parent process. 1 read end in the child process and 1 write end in the child process. My child process here, right now, is stuck because it holds a write end to the pipe that it's trying to read from. And it never closed it. And so it's just stuck. Somebody might write to this pipe. Doesn't know that it's the only one that can write to that pipe, but somebody somewhere might write to this pipe sometime. So I'm going to close FDs at 1. Close the right end of the pipe so I don't get stuck waiting for writers on the pipe. I'm going to make this, and I'm going to run it. And it terminates. Okay, good, yes. The problem here is 100% that in my child process, I did not close the right end of the pipe. This is super finicky. This is super finicky because we have to call pipe here on line 23. We must call it before we can call fork so that these 2 things can be connected to each other. It gets really finicky because if you don't close the right end of the pipe in the child process, the W write, not the correct, but the W write end of the pipe in the child process, we're going to get stuck because somebody somewhere could possibly write to this thing. So I'll post a version of this code up on the course webpage. The very last thing that I want to do with you before you leave today, I know I've got 1 minute left, is to take a quick look at the content for this week. We didn't really get a chance to do this last time we were together. But I want to point out that we will start talking about threads on Wednesday of this week. So obviously we didn't talk about threads today. We will talk about threads on Wednesday. I want to point out, again, similar to other chapters here, chapter 27 is a chapter on the thread API. And so there's a lot of stuff in here that's going to be good for like getting started with how to use threads. The manual pages are also a good way to take a look at this. but there's one important section here that I want to emphasize over everything else. If you skip most of the stuff in this chapter in terms of like, we're going to be using threads to do stuff together a lot, so that's okay. But the one part that's unique to this chapter is about, I'm going to go here to the chapter, and I'm going to go way, way down here to not locks, but condition variables. This is a section that's not really covered or described in the other chapter of the book. So that part specifically is something that is unique to just this chapter. We'll talk about them in class, but this is unique to just this chapter. All right, so at this point, you should be able to write some code where processes communicate through message passing through signals and pipes. You should also be able to a little bit compare and contrast the shared memory and message passing programming models and the relationship as seen through the lens of synchronization, but we will start thinking about this a lot more now that we're going to start moving toward threads and locks with our code. That's it. I hope that you all have an excellent rest of your day, and I will see you all on Wednesday. Bye, everyone.